Hey, Dr. Dan back again. We're going to do something a little bit different today as far as chemistry goes. We're going to be doing some graphing. And graphing is an amazing technique that can be used to interpret data. We're going to be looking at a periodic property that we haven't spent a lot of time looking at so far, the atomic radius. In fact, this is called the atomic volume. You can think of an atom with all those different orbitals, the S and the P and the D and the F and all that stuff, and you get your mind starts swimming around in circles. But we could also think of an atom just like a sphere. Half of the sphere, half of the diameter is the atomic radius. And so the bigger the radius, the bigger the atom, its volume. So that's what we're going to be looking at. But keep in mind there are all kinds of different periodic properties that are out there. We've spoken about a few so far. We could think of the atomic mass. The number of protons and neutrons are going to vary as we move from left to right and from the bottom to the top. That changes as we move from the periodic table from place to place. Atomic radius certainly is going to be changing, and we'll be seeing that as we do our graphing. Boiling points can also not only be seen to change, but also this is a means to predict. What would the boiling point of this element be if we've got this one on this side and this on that side of the square, and the one that's in the middle is going to be somewhere in between. It's a trend that we're looking for. Density, electronegativity, ionization potential, isotopes, and certainly Lewis structures and valence electrons. We have looked at the idea of group 1A, 2A, 3A, 4, 5, and so on, all the way to 8A. So these are all properties that are going to periodically change as we're moving across the chart itself. And it's a means to predict elements that maybe we don't know too much about. So really, really amazing stuff. So how in the world are we going to approach this? Well, pull out some graph paper. That's how we're going to do it. We're going to take a look at graph paper. Your graph paper is going to be 8 by 11. That one looks a little bit funny because that's PowerPoint stuff. But we're going to take this graph paper, and we need to do several things before we even get started with plotting the data. First of all, you better put down the name of this lab on this graph paper itself. Now, I'll tell you a little story. When I was at Akron U, very first year in chemistry, I remember turning in this lab, and I was really proud of this beautiful graph, and guess what I forgot to do? I forgot to put on that thing the title of it. And the next thing I knew, I saw the teacher assistant, the TA, took that thing, crumpled it in a ball, and threw it in the trash can. And he said, Dan, if it doesn't have a name on it, it doesn't mean anything. I'll tell you right now, it got my attention. So don't let that happen to you. Make sure you put your name on there as well as the name of the lab. Both of those things are going to be really important, and it's not a bad idea to put the date down also. Here's the starting point. You got this thing, put down the title. We're going to call this the periodic law. Makes it kind of easy. The other thing I want you to consider is we have two different axes that we have to be considering in terms of how we're going to be plotting our points. There's something called the horizontal axis, better known as the x-axis, and that's the one running, as you can see on this graph, along the bottom portion, so it's running flat across. We also have an axis that's going to be running vertical, and that's going to be known as the y-axis, which is the vertical one. Now we've got the two little axes that are set up right there, and these are going to be the ones that we're going to be plotting the data against. Now here's going to be the big question. If you take a look at the sheet of paper in your lab that has all the data points, we're looking at the atomic number versus the atomic volume. Notice we're going to have a lot of different points to plot. On which axis do you put the atomic number? On which axis do you put the atomic volume? Well, the answer to that question really is based upon the range of the numbers that they give you. If you look at the range of the atomic number, it's going to be between 1 and 54. So we have 54 data points that we're going to have to either put down here or put up along this way. Think about that. 1 through 54 is our range. If we contrast that with the atomic volume, what's the range there? Bigger or smaller? Well, it's way bigger. We're between 30 and 244. Well, here's our puzzle. Do we want to put the atomic number on this side, or do we want to put it on this side? Obviously, the atomic number has less of a range, and the distance going this direction is less. That matches up really, really nice. So we're going to put the atomic number along the x-axis, which means, of course, the atomic volume is going to be along the y-axis. So now that we've got that figured out, we go to the next step. We're going to have to ask ourselves, how many squares do we actually have on the graph, on the x and the y-axis? How do you figure that out? We'll start counting. So you look over here and say, okay, I've got to leave enough room to put my little titles down here in terms of what is the X and the Y. But I'm going to start counting these blocks. How many do I have down here? And I'm going to relate that to the range. How many did I have going vertically? I'm going to have to relate that also to this big range. So we're going to need to count these squares to better understand how to plot these points. What is going to be the goal of our graphing? Now, should it be a good idea to take this and plot this thing in a very, very small section of the paper? And the answer of that is no. We really want to spread these things out as far as possible so it's easy to be able to look at this graph and make some sense out of it. I've had some students who have done this lab and they take like this little tiny portion and they try to graph all those crazy data points right here. That's not going to work real well. You're not going to be able to answer the questions at the very end of this lab by doing that. We also want to make sure that not only are we filling up as much of this sheet as possible, that each one of these squares have the same divisions to it. If we're looking down here at the x-axis, we want to make sure that the blocks are equal to the same number. If this one block is equal to 2 points, this is equal to 2 points. That's equal to 2 points, 2 points, 2 points, 2 points. And there's enough of these squares that are going to accommodate 54 data points. On the same token, if we're looking over here on the y-axis, we want to make sure that these squares are going to be the same. Let's say these are going to be 5 points apiece. All right, how'd you do? Hopefully you're using pencil and not a pen, because when you make mistakes, it's a mess. Well, here's what my graph paper looked like when it was all said and done. I want to take 54 data points for the x-axis. I want to take 244 data points for the atomic volume. How do you make that work on these graph sheets? This is what I came up with. The number of squares that you have on your sheet may vary. Don't necessarily do what I do, but understand the principle. When I went ahead and looked at 244 points, I'm thinking, egads, that is quite a few to try to figure out. And so what I did was I simply counted up my squares and I looked at them and I said, all right, let's go ahead and divide that 244 by the number of squares. And the closest number I could get to where it seemed like it was reasonable, it certainly isn't optimal because I would like to have less than 7 data points per square. But I'm able to fill in this entire side by doing that. And I have a little bit left over here, of course, for my title, and that part's all good. When I look down here with the atomic number, I was able to do every 3 data points per square. And when it all came out to the very end, we have 56. So now we're in really, really good shape. That was the hardest part of this whole lab right here. What you want to do at this point now is go back to your data sheet, and now you start plotting in the points. Well, how do we do that? I'm glad you asked. We're going to start and take a look at these different data points, and we got to label them. Now that's really, really important. Label these things, don't just put a bunch of dots on there and hope for the best. We're going to make a small circle representing the dot for that data point, and we put the symbol of that element. Remember, we have the number of the atomic number itself right next to it, and that atomic number tells you what that symbol actually is. If we have an atomic number of 1, we put that circle right there at 1. Remember, each one of these is 3, so I'm guesstimating that's about 1 right there. And if you look at the atomic volume that's in the data sheet, it says it's about 30. Well, the closest I can come is probably about right there, give or take. Remember, each one of these squares for my sheet is equal to 7 data points. That's pretty much going to be what hydrogen is. Well, how do I know that that's hydrogen? Well, you're going to put the symbol right next to it. So there's our very first data point that we're going to start off with. Strap yourself in because you got 53 more to go with it. Now we go with our atomic number of 2. Go ahead and we follow that 2, that's about halfway in between, that sits right there. And if you look at the atomic volume, now we're going to be seeing that that's going to be falling somewhere right in this range, a little bit more than 91 that we have in this place. So I put down helium. We go to the third one. That's going to be our lithium. Now we have 1, 2, 3. That's going to be that line there. And you look at the range, and it's going to fall somewhere right around that range right there. Now, as you're going through this, don't just simply put the dots and the symbols. Use your ruler and begin to start connecting the dots. By connecting these points, you're going to start seeing a pattern. Remember, the data doesn't speak for itself. It's got to be interpreted. And so as you begin to do this, you're going to start seeing these mountains appearing. This sounds like a good Colorado type experience. Lots of mountains are going to show up. We're going to see periodic properties. What do I mean by mountains? And if you look at this, you'll notice we started with the helium, and we got the hydrogen and the helium and so on, and we move along. There's the atomic number there. On this side is the first ionization energy. So this is not the exact same chart that you're going to be doing. But if you look along the tops here, you'll notice that certain elements are going to be at the peaks. You pay attention to that. Those are going to be some of the questions you're going to be answering at the very end of the lab sheet today. Notice there's also going to be the ones that are sitting right in the valleys. Pay attention to that. Now you can go ahead and shade in underneath this mountain, if you will, that you're building for the atomic volume instead. But this is the idea of what you're going to end up with. Now you have a visualization of the data. And from this point on, once you've got this all completed, then go ahead and try your best to predict what that unknown is. In other words, if you have an unknown between here and here, then look at where that line goes and kind of extrapolate where that would be and see if you can figure it out. So with all that said, have fun. It's a pretty amazing way to understand the world around us by graphing. And you will find that you'll have professors in college that'll ask you to do this. So get good at it now so you get that easy A when you take it in the laboratory in some place in the future.